In the world of chemistry, reactions occur all around us, some releasing energy, others absorbing it. But how do we measure this energy change? How can we predict the energy involved in this reaction that can't be directly measured? This is where Hess law comes into play.
Hess law, named after the Swiss chemist German Hess, is a principle in thermodynamics that states the total change of a reaction is the same, regardless of the pathway taken.
Think of it like a road trip. Whether you take the highway or bumpy road, you end up at the same destination having traveled the same total distance. Similarly, with Hess law, the total energy change from start to finish remains constant, even if the reaction follows different routes.
So for today, we're going to tackle about what is Hess law. So first, let's proceed to the direct pathway, in which we have 2 carbon monoxide plus oxygen gas yields to 2 carbon dioxide, in which we need to find the enthalpy change for this reaction. In order to proceed, we must have our indirect pathway, in which we have 2 carbon plus oxygen gas yields to 2 carbon monoxide that has the enthalpy change of negative 221 kJ. And next is the carbon plus oxygen gas yields to carbon dioxide, in which has the enthalpy change of negative 393.5 kJ. In order to proceed, we must manipulate the equation in the indirect pathway in order to match the equation in the direct pathway.
As you can see in the first indirect equation, the 2 carbon monoxide is in product position and in direct pathway is in reactant position. So we need to manipulate the first indirect equation. In manipulating the equation, we need to transfer that 2 carbon monoxide in reactant position. And we come up into 2 carbon monoxide yields to 2 carbon plus oxygen gas. In second equation, we need to multiply it by 2. So we come up to 2 carbon plus 2 oxygen gas yields to 2 carbon monoxide.
In the first equation of the indirect pathway, since it is manipulated, we also need to change the negative side of the enthalpy change to positive. Therefore, it is positive 221 kJ. And in the second indirect pathway, since it is multiplied by 2, we also need to multiply the enthalpy change by 2. Therefore, it is equal to negative 787 kJ.
Next, we need to cancel out the same element in this equation in order to get the final equation. So we need to cancel the 2 carbon, 2 oxygen gas, and we can now get the final equation. It's 2 carbon monoxide.
After getting the final equation, we must sum up the 2 enthalpy changes of the indirect pathway, in which it will be negative 566 kJ. Therefore, the total enthalpy change of this reaction is 566 kJ.
Real-world application. From the energy we use to heat our homes to the medication that keep us healthy, Hess law plays a crucial role in our daily lives.
In power plants, Hess law helps engineers predict how much energy is released when fuels like coal or natural gas burn. By understanding the heat change in these reactions, they can design more efficient systems to generate electricity. These principles holds true because enthalpy, a measure of heat content, is a state function. It only depends on the starting and ending points, not the route taken.
In the pharmaceutical industry, Hess law is used to design efficient chemical processes for drug production. By knowing the energy involved in each reaction step, chemists can optimize manufacturing, saving time and resources.
From energy production to healthcare and environmental protection, Hess law is more than a concept, it's a tool that helps us solve real-world problems, making our world safer, more efficient, and sustainable.